Hello, I'm recording on a snowy day. It snows a lot outside. I hope everyone stays safe and has no problem with the snow. So let me continue what I have done last time. The theme we talked about last time was the distinction between population and sample. Just to remind you of what we have done, remember that one important concept in statistics is the experiment, because a randomness is generated from an experiment, and we can learn about the randomness by observing, by repeating the experiment. So then, conceptually, we assume that there is the limit in which where the experiment is repeated for an infinite number of times. It is not possible, but we just have in mind that is the population. On the other hand, what you observe is just a finite number of repetitions of the experiment. So we call that sample. That is exactly what you have, what you observe in the data. So the distinction between the population and the sample is important because the population is what we want to know, what we are interested in. We would like to understand the distribution or the expectations related to the population, but it is not available. We cannot observe infinite number of experiment results. So we use the sample. We use the sample to infer about the population. That is statistical inference. And second, we the distinction is important because then how can we justify? So we only observe just a part of a big group. Then how can we justify our estimator, like our inference methods? Then to do that, to justify our estimation method or to evaluate how good we are doing, we will study the relationship between the sample and the population. That's to understand those relationships, you need to distinguish them. I have gave you the simple example with coin toss, and and this is the serious definition of those terms, but the basic idea is already delivered in casual words. So if you are interested more serious, rigorous statistics, uh, study yourself. So then notations, typical notations. Usually in many cases, like parameters are usually denoted by Greek letters. Greek letters are like alpha, beta, gamma, delta, epsilon, da da da. So mu, sigma squared, theta, beta are typically used for parameters. Only the maybe the an exception is epsilon here. So epsilon is a Greek letter for E, but it is not a parameter. Later you are going to see this stands for errors. So except for epsilon, most of the parameters are denoted by Greek letters. In general, it's not a rule. So then sometimes to distinguish just one possible value of the parameter or the true value of the parameter, we use subscript 0 so theta 0 is a true value of theta and beta 0 is the true value of beta. So this is another common notation, and these are parameters. So mu and sigma squared, mean and variance. These mean and variance are obtained from the population. So we assume that these guys are calculated from the population, but then there must be their counterparts from the sample. The sample counterparts are x bar, which is the sample mean, and s squared, which is the sample variance. So the reason, by the way, later on, you will soon realize that the notation is not unified well. They are not consistent to each other. The main reason is because the sample mean has been used like many years, like several hundred years, I guess. But the theory for sample mean, the distinction between the sample mean and the population mean, it's not as maybe 100 years ago. Well, it has been developed relatively recently. So that's why so theory comes after the practice. So the notation used in the practice may not be consistent with the framework uh, laid out by the theory. So please understand, I have no power to change that. I don't like the notation either. So anyhow, distinguish the sample mean and the population mean. Conceptually simple. And theta hat and beta hat are usually estimators for theta and beta. And I use expected value of x and variance of x. So I explicitly show what I'm doing, like expectation of x is the population mean, and variance of x is the population variance. So this is the notation, and typically in a statistical inference process, the first thing you have to do is to define your question, or you have to define what you are interested, what you want to estimate, what you want to infer about. Like so, that's the first thing, of course. And second, you have to have a random sample. You have to collect data, and third step is to calculate some statistics, which is an estimator, statistics from the random sample, like calculating the estimator or calculating the test statistic or calculating the standard errors, confidence interval, p-values, those guys. So based on your data, you have to do algebra. Then finally, statistics theory should follow. So you have to show that your estimator is, for example, unbiased, or you want to show that your estimator is efficient or consistent, um, like that. So we need to the statistics theories justify your method or evaluate how good you are. What is the potential error probability, and what is the standard errors, and if you can do better or not, something like that. So that's the final step. And as I said, these methods are have longer history than the theory usually. So the theory follows the development of the method in the past, like 100 years ago. So um, there may be some kind of inconsistencies in notation. Okay, let me give you an example, more concrete example. Think about linear regression. I believe you learned linear regression somewhere before, and this is a typical form of linear regression model. So in here, what we are interested in is beta 0, beta. So we learned that y is generated from this linear relationship plus error. And then x and y are observed, and we are interested in beta. The effect of x on y is captured by beta. So that's our parameter. So we define the parameter, and then you collect the variables, the random variables, the sample, x and y, pair of x and y is one observation, and then calculate beta hat. There are many different ways, like maybe you have learned ordinary least squares method, OLS, is the most common way to estimate that, but there are alternative ways like HEG estimator, GLS estimator. So anyhow, you may use one of them, one of the methods, and then now you have to show that, for example, your estimator is unbiased. Your estimator has a certain limiting distribution, has certain standard errors, something like that, consistency, and like efficiency, like blue, the best linear unbiased estimator. So those kind of evaluations of your estimator is the last step. So this is how we proceed, how we conduct statistical inference. And I would like to emphasize then the idea was we would like to infer about the population using the sample. And I told you that the relationship between the population and the sample is important, right? Then what is the required assumptions? So it is not always it won't be correct all the time. Sometimes if your sample is wrong, then your estimator will be wrong. So we require assumptions, which is the famous IID assumption. Um, so the basic idea is your sample, to infer about the population from the sample, your sample must be randomly chosen. It cannot be biased. If it is biased, then there should be a problem. So random sampling is the assumption. Actually, it's tautology. So you need to have a random sample which should have been randomly sampled. So they are the same words. Anyhow, then what is the random sampling? The random sampling is the IID assumption. So you repeat experiment. You repeat an experiment which is choosing a random object from the population. So randomly choose one. Choose one ball out of the box. The box is called the population. Choose one ball and observe the number on the ball and repeat that. So the number of repetitions is the sample size of the random sample. And in this repetition, the repetition has to satisfy two assumptions. That's I will explain that later. And the results are denoted by x1, the first outcome is x1, and in the second experiment x2, and nth experiment will generate xn. So there are n observations, and we call that as a group, as a set, this vector of observations, the matrix or set of observations is called a random sample. So when you repeat the experiments according to the IID assumption, then the results make a random sample and denoted by this way. And the best example to understand this is the survey. So choose a random person and ask about like income or education or like job, where they live, something like that, and repeat that. Choose another random person, another person, another person, blah blah blah. So in this case, even if in this case, in the survey the population is a finite number. So like in the United States, I don't know what's the population. So anyhow, it's finite. It's not an infinity, but there is no difference. Anyhow, we never observe the population in statistics, so there is no problem to consider to view the population as an infinite number of observations, right? Even if the population is actually finite. Then what is the IID assumption? The IID assumption is the requirement for a random sample. The first I means identical distribution. Second I means independent distribution. So identically and independently distributed. So identical distribution means that when you repeat experiments many times, each experiment must be from the same distribution, which is obvious. If they are different, so you may understand it as all the observations must be from the same population that you are interested in. So for example, suppose that you are interested in the distribution of wage of women in the United States. So women in the United States. But suppose that the first observation is a woman in, say, South Korea. Of course, then the distribution in the South Korea would be different from the distribution in the United States. So it's a problem. And so the first one is from South Korea, second one is from the United States, and say third one is a male. That's another problem. So in that case, there is no the distributions are different and they are from different populations. So what you estimate is uncertain, right? That is the first assumption. All of the observations must be from the same population. And second, independent. The first one should not affect the second one. the result of the first experiment should not affect the result of the second experiment. Like for example, when you choose one person and survey the person and just ask the same questions to his friends or her friend, then the effect of the result of the first survey affected the second one because friends must be correlated in some sense, in some way. So the first one and the second one would be correlated, then it violates independence. So the first and second and every observations has to be independent of each other. So IID assumption is so basic, I'm going to assume this throughout this course. So always whenever we observe something, IID, they are IID. And another interesting thing here is so heteroscedasticity of regression model is a violation of identical distribution assumption. So heteroscedasticity implies that the variance changes as x occurs observations. So it means that distributions are not identical. But there are methods to correct, to handle the heteroscedasticity. But I'm not going to consider this seriously in here because we aim a more general framework in this course. So heteroscedasticity is just a special case, and frankly, I don't think it's super important relative to other topics I'm going to cover. So I'm not going to spend much time on this example. And there are some, even if I'm going to assume IID throughout the course, but there are examples where IID assumption is broken. For example, time series data. Today's GDP is correlated with yesterday's GDP. So all the observations, if you observe, like say, GDP from the past, say 50 years, then they are correlated to each other. So IID assumption is broken, and then how to handle those time series is another question. So I'm not going to cover that in this course. You will, if you're interested, you are going to take time series course later. So that will cover this topic. So the video becomes a little bit longer, but so I'm going to stop here.